Hi, welcome back. So now we have learned how to add two OH groups, two alcohol groups, anti, right, to a double bond. So they are on opposite sides. They end up on opposite sides of a double bond. We can do that, recall we could do that by just first doing an epoxidation reaction, make this three-membered ring with an oxygen, and then opening up the epoxide with backside attack, right? That gives us an anti dihydroxyl, di-OH compound, diol. Now what, sometimes you might not want to get an anti-diol, you might want to have the hydroxyl groups on both sides. And guess what? There is also a reaction, special reagents which can do this. You should know this reagent. So you use, in this case, we're going to get not an anti addition but a syn addition instead. And so we are adding the two hydroxyl groups to the same side. So it means syn to the double bond. I'll give you a second to write this. So we added syn to the double bond. We use a special reagent. And the reagent I'd like you to learn for this reaction is osmium tetroxide. Osmium tetroxide. And yeah, this adds both hydroxyl groups at the same time from the same side. Okay, let me show you the mechanism. We are starting off with an olefin. Six-membered, again, we're drawing a six-membered ring olefin here because then you can see that both hydroxyl groups end up on the same side, because we can see whether they end up cis or trans, right? If they're added from opposite sides, they would end up trans, the two hydroxyl groups. If they're coming from the same side, they will end up cis. That's why we use a six-membered ring here to demonstrate it. So that's our starting material, and so now here's how osmium tetroxide looks. It's an osmium element with 4 oxygens around it. So this is technically violating the octeteral, but it kind of also isn't, because it's a heavy element, and you remember from Gen Chem that you can, for heavy elements like sulfur or osmium or phosphorus, things like that, you can have more than 8 valence electrons. Okay, so that's what's going on here. You can never violate the octeteral for carbon or hydrogen or these kind of first and second row elements, but for the larger ones you can do it. Okay, so this is the osmium tetroxide, and the oxygen atoms in the osmium are electron deficient. This means the double bond can attack them. Again, double bond, like always, it's acting as the nucleophile. It's attacking one of these oxygens, and then for the oxygen not to violate the octeteral, you have to push the double bond onto the osmium. And then it's a cyclic arrow pushing mechanism. By now, the other oxygen at the same time is attacking the carbocation, which is forming there at the bottom of carbon of the double bond. Okay, so it's a cyclic mechanism. You should remember this. Now, if you follow through the arrow pushing, you can see what happens. So now, assuming that the osmium tetroxide came from the front, it gives a syn addition right from the front, and then both hydroxyl groups, well, both oxygens there, which are now bound to the carbon atoms of the double bond, are coming to the front. Okay, and we indicate this with wedges, of course. Then you see there's a lone pair now on the osmium. That actually means the osmium has gotten reduced, while the carbons have gotten oxidized technically. And so now in a second step, people generally use another special reagent to take off the osmium and convert this ring structure into two OH groups. But technically, what we formed here is called a cyclic osmate ester. Okay, I want to give you one caution of warning here. If you ever use osmium tetroxide to do this reaction, it's a really great reaction, gives very high yields, but it is super, super toxic. It causes cataracts in the eyes. The osmium tetroxide is actually a gas, and it has a fairly low vapor pressure, so it sublimes, it becomes a gas, and it will go right in your eyes. You have to be super careful with that stuff. Okay, but a very useful reagent nevertheless. So now here's the second step. To get rid of the osmium, what you do is you react the cyclic osmate ester you cleave it with a special reagent which is called sodium sulfite. Okay, it's not sodium sulfide, it's sodium sulfite. And that forms two OH groups. You don't have to know the mechanism of this step for now. All I want you to remember is this reagent that we can take off the osmium. You just have to recognize and remember the reagent. So no mechanism, just the reagents, and here's how it goes. That's the reagent. Sodium sulfite in water is generally used. So if we draw out the whole thing, and this is the cyclic osmate ester we're starting with. Now we are using our, it's actually a reducing agent, our sodium sulfite, and in water. And now we're just forming just two hydroxyl groups which have been added in a syn fashion from the same side of the double bond. Of course, in this case, we're forming an achiral product because it's again a meso compound which has a mirror plane going through the molecule. Center of the molecule coming out of the plane of the board cuts right through the molecule, and this is why it's achiral, so we don't have to draw the enantiomer. Right? There's no enantiomer of this compound. It's an achiral meso compound. So again, I would like you to practice this reaction with a conceptual checkpoint 827. So I will, now is a good time to ask your TA some questions, and we will reconvene in a minute or so.